Why didn't you ask that a couple of minutes ago? You got to fly. Be really fast. Let's go. Okay. So yesterday we did a do it that was a lot like this, and we noticed that the first 6 words of all of these questions are the same. Write the equation of a line. Write the equation of a line. Write the equation of a line. The minute you read the words, write the equation of a line, what automatically pops into your head? Very good. Y equals mx plus b. What does m stand for? Slope. Good. What's b stand for? Y-intercept. Very nice. You know, I talked to my physical therapist yesterday about my comparison between doing homework and physical therapy. And he said, you know, it's really a good comparison. He said, it's a lot like that. And then he went on to torture me for the next little while. Okay, so we know all begins with y equals mx plus b. And it's going to end somewhere close to that, too. So this one says, write the equation of a line whose slope is 3 and whose y-intercept is 4. So I'm going to get y equals something x something at the end. Now, what letter means slope? Does the m mean slope or does the b mean slope? The m, good. So what is the slope supposed to be here? 3. So I'm going to put a 3 in the first box. And what's the y-intercept supposed to be? The b. -4. So I put a -4 there. And my final answer is y equals 3x minus 4. Now, how many of you guys just know that this question's on the next quiz? After doing this multiple days in a row and to do it, you know I'm coming back with it on the quiz to make sure that you really are 100% on this. Talia, are we okay on that? Okay. Next, write the equation of a line parallel to this guy, but the same y-intercept as that guy. Now, when we think about parallel and lines, what do we always remember about parallel lines? There really are 2 things. Michael?
They have the same slope.
They have the same slope as 1, and what do you know about how they look?
They're not touching.
Yeah, they're not going to touch. They're the same distance apart the whole way. So, in this case, since the slope is the same, I know that my slope has to be 2. But it says it has the same y-intercept as this guy. What's the y-intercept of the second guy? 3. So I'm going to get y equals mx plus b. And what's the m, everybody? 2. And what's the y-intercept? 3. So my answer is y equals 2x plus 3. Now, how many people got both of those right? How many people got 1 right? Okay, so we're looking pretty good. All right, now, number 3 says to write the equation of a line that passes through 2, 0, and 4, -5. This is an important question because it's going to relate a lot to what we do today. And what we do today is really where this has been heading all along, okay? So, 2, 0, and 4, -5. 2, 0, and 4, -5. So here's 2, 0, and here's 4, 1, 2, 3, 4, 5, -5. So, look, there's a slope. A slope, another way to think of slope is rate of change. What's another way to think of slope? Rate of change. On a straight line, it's a constant rate of change. Ready? To get from my blue dot on the left to my blue dot on the right, I have to go what? Down 5 and then over how many? 2. So if I do it this way, if I go over 2 more and then 5 more, I get this dot. And then I could do it here again, 1, 2, 3, 4, 5, and then 1, 2 here. So here's my line. It's a little bit cockeyed there, but it's as good as it's going to be. So there's a picture of my line. And since the question says to write the equation of a line, what automatically pops into my head every single time it says write the equation of a line? Y equals mx plus b. Good. Now, the only difference between this question and the other questions is on the other questions, you had to analyze an equation and figure out m and b. This time you have to analyze a picture and figure out m and b. Now, the y-intercept is b, but on the graph of a line, how do I find b? Talia?
Whatever is on the y-intercept.
Yeah, wherever it crosses the y-axis. That's why we call it the y-intercept. So in this case, it crosses at +5. So I know I'm going to get +5 at the end. Now, how do I find the slope by using the picture? Mr. Middledorf? Yeah, or in this case, it's actually like a drop over run, right? Because we're going down. So I'm going to go, as I said before, down 5 over 2. So it's y equals down 5, the down is negative, over 2x plus 5. Okay? Now remember, with slope, we have rise over run is a good way to look at it. Another way is the change in the y over the change in the x. That make it look more like an x. And a third way is this formula, which don't let the twos and ones bother you. It's the y from the second point minus the y from the first over the x from the second minus the x from the first. All of those are important. Rise over run. All of those are there. Rise could be drop if I'm going left or right. All right, any questions about this? All right. So that's really the basics of equations of a line. Now what we're going to do today is we're just going to shift a little bit and we're going to talk about real world applications. We're going to take the same exact idea and see how this works in real life. So let's turn the page. And we have one question we'll definitely get through, and I think we'll get through a second question too. And I think you'll see how their real life questions work. Who wants to read question number one, nice and loud? Someone's got to read question one. Let's go. Little volume here. Talia, fire away.
Miss Wilson's oven increases in temperature at a constant rate. After 5 minutes, the oven temperature is 150 degrees. After 10 minutes, the oven temperature is 200 degrees. In the space below, graph the line representing the change in temperature in the oven over the first 15 minutes.
Nice job. Okay. Do you notice anything different about this particular problem compared to all the ones we've been working on so far? Go ahead.
It's like only one box in that thing, though.
Oh yeah, the picture is one box. We'll get to that in just a second. That's the second thing, actually the third thing I want to talk about. What else do you notice about this problem? What about the numbers? Yeah, they're pretty big, right? Right? Didn't we do like slopes of 2 and y-intercepts of 3? What are the numbers here? 150, 200, 10 minutes. This is getting pretty big. Okay, so that's the first observation. And do you really want to like mark off 150 or 200 boxes? That'd take a little while, right? So we're going to have to deal with that. I want to talk about this term here, increases in temperature at a constant rate. Whenever it says a constant rate, that means a straight line. What does a constant rate mean? Straight line. That's very important that you pick up on that. What's constant rate mean?
Straight line.
All right. Now, the next is what Talia said before. It's only one part of the graph. Look over here. See my graph board? That's divided into what we call the 4 quadrants. Every graph you've done so far has had 4 quadrants in it. That's because the x could be negative and the y could be negative. So I need to be over here for x negative, y negative, over here for x negative, y positive. All of a sudden, I'm giving you a graph, and the only thing you can see on this graph is positives. Let me ask you a question. When is the last time that time was negative? Do you ever get negative time?
Negative time?
Yeah, negative time.
Like,
Hey, what time is it, Eric? Oh, it's negative 2 o'clock. When's the last time you ever heard that? No, ain't happening. What about ovens temperatures? When's the last time an oven was negative 100 degrees?
No.
Doesn't happen. Leah's Italian. She's all over the cooking aspect of things. Now, ovens are positive, time is positive. So I only need the part of the graph where the x's are positive and the y's are positive. What part of the 4 quadrants has x's positive and y's positive? The first quadrant. So that's why I only put this here. Now, sometimes you're going to need the first and the third quadrant. Sometimes you might need the first and the second. All depends on the problem, and that's part of the things you need to figure out. All right, this is talking about time, and when it talks about time, I think it's important to realize that the numbers for time are fairly small. They're talking about 5 minutes, 10 minutes, 15 minutes. I can fit those numbers on this graph. So the first thing I want to do is I want to come over here and I want to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So I put those on the graph. That's the first thing I need to do. And what did we say those numbers were? Is that the oven temperature or is that time? Time. So you can call it time or you can call it minutes. I wrote MIN. Okay, you can call it whichever one you want, but you should label whichever one you want it to be. Okay? Now, temperature. The temperature in this problem, we talked about numbers like 150 and 200. Do you really want to write 150 and 200 marks on this? No. Furthermore, wouldn't it take like an enormous piece of paper?
Yeah.
Yeah. So I'm not going to want to use a scale of 1 box equals 1. In fact, I'm going to go with a scale of 1 box equals 10. So instead of going over here on the left and writing 1, 2, 3, 4, 5, I'm going to go 10, 20, 30, 40, 50. And then once I've established that scale, in the effort to keep it neat, I'm going to go like this. Ready? Just watch this 1 second before you keep writing. Watch. 60, 70, 80, 90, 100, 10, 20, 30, 40, 50. So I'll go like that. You can keep going now. And you'll notice I labeled that vertical axis temperature. Okay, now, the next thing that we have to realize is that we have to start marking our graph. Didn't it say at 5 minutes you're at 150 degrees? Right? So let's take our pens and let's find the point where 5 minutes is 150. There it is. Make that mark. Now remember, what did we say before a constant rate means? Straight line, good. So now, find the point where 10 minutes is 200 degrees. Okay, and once you get the point, 10, 200, and mark it on your graph, you should be able to draw a straight line. 10, 200. Now here is my straight line, but I'm going to warn you about something. Ready? You better stop right on that axis. Do not go past the axis. Why is it so important not to go past the axis?
It'll beat you up.
Because I'll beat you up? No, that's not why. Go ahead.
Because it'll turn into a negative.
Yeah, time would turn into a negative. And we just got done saying that you can't have negative time. So on one of these graphs where it's first quadrant only, and you were talking about something like time, where time can't be negative, do not go past that mark. All right, now did you notice how it looks better on your paper than mine? Because I ran out of room? Okay. Now, the next question says, what's the temperature after 12 minutes? And there are 2 ways to do this. I'm going to pause for about 30 seconds and see if you can figure out one way to do it. What's the temperature after 12 minutes?
We have to get like what's temperature at 12 and 13.
Just 12.
Just
Tell me the
12.
temperature at 12. Talia, what do you think?
I think it's 220.
I think you're right. Okay. Now, the way we can do that is as follows. Isn't it true that at 10 minutes, and I'm going to change color here for a second. Isn't it true that at 10 minutes we were at 200? So at 11 minutes I'm at 210, and at 12 minutes I'm at 220. Now another way to do it is this. Go down on your graph and everybody put your pencil on 12 minutes. Now very, very lightly, go up your graph until you hit the graph. Okay? Then go over and see what number you're on. What number are you on? 220. So that's one way to do it, okay? That would be called the analytic approach. But one of the really cool things about math, one of the things that separates it from all the other subjects, is, like, who remembers what manifest destiny is? What's manifest destiny?
I think it's when you move west.
Yeah, it was, manifest means apparent in the English language. So it was our apparent destiny that when the Pilgrims landed at Plymouth Rock, we owned all the land to California.
That's awesome.
Now, how do you think the Native American Indian felt about that? I think they had a slightly different opinion. And I think if I held a little discussion about, oh, what's going on here? Oh, you went up by 50s? You can't do that. If you're gonna start going up by 10s, you have to keep going up by 10s. You can't change the scale, okay? If we had a little discussion about manifest destiny, and on my right-hand side, if I put an American Indian, on my left-hand side, I put a Pilgrim, and I ask them about American or manifest destiny, you're gonna get two very different responses, okay? The really cool thing about math is no matter how you come at something, there's gonna be agreement in the answer. What's right is always right. Here's another wholly different way to do it. Remember how we had the third question on a do it where we looked at the graph and we figured out the equation of the line? Let's do that this time. And the equation of a line is y equals mx plus b. So I know I'm going to get y equals, I know there's going to be an x there, and I need to figure out the slope and the y-intercept. I always like doing the y-intercept first, even though it comes second, because it's so easy to figure out. What's the y-intercept on this graph? Just look at the graph. What's the y-intercept, everybody? 100, good. So I'm going to put plus 100 at the end. Now, look at your graph, and what is the slope? Go ahead.
5/5.
No. Good try. You took the wrong bait, though. You do go up 5/5. You're right about that. But every box is not 1. When I come over here, and I go up 1, how much am I really going up?
10.
10. So it's up 10 over 1, up 10 over 1, up 10 over 1. Does that make sense? So my slope here is actually 10. My average rate of change, if you will. My constant rate of change. Now, which is the x? Is the x the minutes or is the x the temperature? Look at your graph. Isn't this the x-axis down here? Is that minutes or temperature? Minutes. So I'm going to put the 12 in for the x. So y equals 10 times 12 plus 100. Somebody tell me 10 times 12. Go ahead. 120 plus 100. So then y equals 220. Now I find this to be pretty cool. The fact that I can look at the graph and come up with the answer analytically, that was the first way, or the fact that I can substitute some numbers in and I can come up with the number using algebra. Okay? Any question about that? We looking good? Everybody got it? Okay, let's try one more. Hopefully we'll get all the way through this. The last class didn't quite get all the way through this. We got till 11:30, so I think we will. I need somebody else to read. Leah, again.
Recently, this new Central Asian Shepherd puppy Gibbs is quickly gaining weight. At 8 weeks old, Gibbs weighed 15 pounds. At 10 weeks, Gibbs weighed 27 pounds. Make a graph of Gibbs' weight gain, assuming he gains weight at a constant rate from ages 8 weeks to 14 weeks.
Okay. Now, constant rate, what does that mean? Straight line, good. Now, you're going to need to set this graph up. First off, is Gibbs ever negative old? No. So I don't need the negative half. And is Gibbs ever negative weight? No. So I don't need the bottom and I don't need the left-hand side. So this is a first quadrant only graph. The numbers are getting pretty big. We're talking about 27 pounds. So do I want to use 1, 2, 3, 4, 5 on the left? When I do vertical, do I want 1, 2, 3, 4, 5? No. My advice to you is to go up by 3s. Can anybody guess why I want to go up by 3s? Go ahead.
Because you can divide 3 into 15 and
That's right.
27.
3 goes into 15 and 3 goes into 27. So each box being 3 will be pretty easy to work with.
The pounds are going on this side.
Yeah, the pounds will be vertical, and horizontal will be the number of weeks. Okay, draw your graph. Go over it in just a minute.
What can we go over for weeks, like two?
I would do one by weeks, because look, we're talking about numbers that are like 14 and less, and I think all of those can fit on there. That's really the determining characteristic. Do the numbers fit? Okay.
Is it okay for them run like this? Like,
Yeah, absolutely.
so would my dots be the same as yours? Or?
Yeah, they actually are the same. It's just that your graph's a little more spread out. Okay, so I have my two graphs, my two dots drawn, and the truth is that I didn't pick the best numbers on this because you're not going to really get a y-intercept out of this, so we'll just kind of ignore that part of it. But I noticed that my slope here, I'm going up 4, 2, so that's 1, 2, 3, 4, 2. So here's my line, and it wants to know how much did he weigh at 9 weeks. Well, at 9 weeks, he's right here. And if I go over to here, what's my magic number at 9 weeks? How many pounds? 21, very good. So at 9 weeks, Gibbs weighed 21 pounds. Once again, watch it, ready? Let me use a different color here. Everybody watch so that you don't miss this, Gabby. At 9 weeks, I go to 9 weeks, I go up until I hit the graph, then I go over, and that puts me right here. 15, I'm going by threes, 15, 18, 21. So it's 21 pounds, okay? Then it's how much did he weigh at 14 weeks? Now 14 weeks is all the way over here. 10, 11, 12, 13, 14. So I'm gonna go up to the graph here. And I still do 2 over 1, 2 over 1, 2 over 1, 2 over 1. It should be right here, I'm a little bit low there. And I go across, and what do I get for the weight at 14 weeks? What do I get, guys? 51 pounds. All right, now, this graphed a particular part of a dog's life. When a dog's a puppy, does it grow fast? Right, you ever see puppies, do they grow pretty quick? Yeah. What about when a dog's older, does it grow quick? No. So in reality, this graph might look like a straight line and then start to taper off. So it won't go straight forever, but during a puppy part of its life, it grows pretty quick. All right, you guys are good, you can start your homeworks. Every time you see the words, write the equation of a line, what pops into your head? y equals mx plus b. And in these real-life applications, you have to check and see, do I need stuff in the second quadrant, the third, the fourth, or is just the first good? All right.